So let's jump right in. Yesterday, we introduced the idea of using these convolutional neural networks that are a bit of an extension on from the basic fully connected neural network that we started talking about originally. And we showed how they could be used for this task of image classification. Um, and, again, when we talk about image classification, we're really talking about predicting what the subject of an image is out of a specific set of classes. There are some pretty big limitations on this. The first is that, in general, these models were mostly working with pictures where there was a clear central subject figure or item, and that is the thing that they were being asked to identify. Crucially, there would only be one single object in the image, so it was very clear what the model was supposed to be able to distinguish. And when I highlight those things, it might start to seem a little bit obvious that there's a lot of real world tasks where that's just not enough, where we kind of need a little bit more complexity in the system to be able to make that really useful. Because of course, in the real world, we're often not going to be able to take the time to take, a very clear, focused image where the thing we care about is right in the center, and there's nothing else in the image that, might be relevant to us as well. So tonight we're going to go beyond that image classification task and talk about some of the other tasks that happen in computer vision that are maybe a little bit harder, but accordingly a little bit more useful in the real world. So this sort of grid shows us how we can move on from the basic classification task. And in the top left here is what we talked about yesterday. So this is classification where we have, a single object in the center of the field. It's obvious what we're looking for. And we're just saying, what is that thing that we are trying to identify? Uh, Going one step further, we can add what's called localization to the model. And so localization is saying not just what is it, but where is it in the picture. And so we can see here that it's drawn this bounding box, as we call it, a grid around the thing that we are classifying. So both we're saying that it's a cat, and we're also saying, or sorry, it's not a cat. My model just failed. We're both saying that this is a dog, and then we're also saying where the dog is in the picture. We can extend that again to multiple objects. And so this is called object detection. So it's detecting because we don't know if they're there at all. And so now not only are we, saying what the subject of the image is, but we're identifying as many subjects as we think there may be in the image. So here, fairly obviously there's two cats. So we're drawing bounding boxes around each of them, and then we're saying that these are cats. That's how we're classifying them. To go even another step forward, we can go beyond the idea of a bounding box, and we can actually say, what are the individual pixels that belong to this object of class cat in the pixel. And so this is a similar thing, but it's more specific in which parts of the image are actually the object that we care about or the subject. And then one final extension past that is instance segmentation. So here now, not only are we saying that all of these pixels are of belonging to cat, but also we're able to say there are actually two separate cats. And here's where the line between them is in the image. So here's where one cat ends and the other one begins. And so this is sort of the hardest version of the problem that we're going to look at tonight. So we're going to walk through each of these different steps and each of these different kinds of task and talk a little bit in more detail about how they're approached and how we solve them. So the first is simple localization, so drawing that bounding box around an object, which is actually, as we'll see, a kind of regression task. Then we'll move on to talking about detection algorithms that are able to, detect an arbitrary number of subjects in an image. We'll talk about fully convolutional networks. So, the networks that we looked at last night, at a certain point, we have a flatten operation, and then we have, a linear set of layers. And in a fully convolutional network, we never do that. We just keep it as two dimensions all the way through to the end. And then lastly, we'll talk through semantic and instance segmentation. So these two tasks where we actually identify pixel by pixel what belongs to the class that we're talking about. And instance segmentation, we also distinguish between multiple subjects of the same kind. Okay, so let's get started. So the first thing that we're going to talk about is this idea of localization. And so again, in the basic task for localization, there's just one object that we're trying to identify in the image. We're trying to draw a box around where that object is. In order to do this, we need to predict a set of coordinates. So this would be like a starting coordinate, maybe in the bottom left, and then a width and a height for the box. It could also alternatively be like a bottom left and a top right coordinate. Either of those systems work. But the point is that we need to predict 4 values in order to describe the shape and position of this box in the image. And the quality of these predictions is evaluated using a metric called intersection over union. And so what intersection over union calculates, let's say that our prediction is here. We first calculate the area where these two boxes intersect. So what is the area of the overlap? And that's the intersection. And then we secondly calculate the union. And so the union is the total area of these two boxes as if we combine them into a single shape. So as if we combine them into a shape that kind of looks like this, then we calculate that area as well. And so the idea here is that if the prediction for this bounding box is perfect, then the intersection and the union will be exactly the same as each other, because one box will be directly on top of the other. And if the prediction is nowhere near the correct answer, so if there's no overlap at all, then the top value, the intersection, will be 0. And then it doesn't even matter what the union is because the total value will be 0. So it goes between 0 and 100%, and it essentially is just giving us a proportionate amount of overlap corresponding to the sizes of those bounding boxes. So, making this is straightforward with a convolutional neural network. We take in the image as our input data, and we predict these 4 coordinates. And then we compare the values of those coordinates with the actual true value, and we compute this intersection over union. That loss is then used to update the training weights, and we update the model until it gets a good answer. And this is a regression task because we're predicting what are functionally, real values. They're like the coordinate values in the system, and they can be anywhere in the range of this image. So there is a maximum and a minimum, but they can be anywhere in that range. And the box can be any size, right? Because we don't know how big the subject is going to be in the image. Now, in practice, it's usually not enough to just say where the subject is. We also want to say what the subject is. So there's 2 different tasks, right? The localization, saying where the subject is the regression task. And then saying what the subject is the standard classification task that we've seen already for computer vision. And so the way that we're going to tackle this problem is to actually split off our network in 2 different directions, one of which is going to predict the class that the subject belongs to. So is it a dog? Is it a cat? Is it a capybara? And then the other side is going to predict those bounding box coordinates. So the network starts with a shared set of convolutional layers. So the patterns that we identify in the image are shared between both of these remaining steps at the end. And often in practice, this is going to be a pre-trained convolutional neural network, something like ImageNet on ResNet or something like that. Once we have these features, once we have the output of this convolutional layer, We then use that as the input to what you can almost at this point think about as two separate neural networks that take these convolutional features and then make their corresponding predictions, which are separate to one another. In general, the way that we do this is that we train these two parts separately to one another. So we have, you imagine this as one network end-to-end up here, and then another network end-to-end up here. But there are ways that we can actually train the network entirely as a single unit as well. We just have to have two different error functions that we combine together. But of course, when we actually want to go and use the network, we'll use both of these heads together so that we get both the bounding box and the classification of what is in the image. So, to sort of formalize, we have a set of classes that we can choose between, so that C possible classes, and then we have 4 output values to dictate the position and size of this bounding box. And this is going to predict a fixed number of objects. So in this case, we're talking about one object. We can generalize to predicting multiple objects. We just have to change the number of coordinates we're predicting and the number of class values we're predicting. Now, a downside of this system is that there isn't a direct link between finding the bounding box and saying what the subject of the image is. And so what I mean by that is that we're not guaranteed that this part of the model down here that has the job of choosing the bounding box, it might choose the dog because that's a reasonable prediction. But then the classification head up here might look at the same image and say forest, if that's one of the classes that it's been trained on, because the image is clearly of a forest. And so these two things are not connected to one another. They don't have an influence on one another. And so what we would end up with is this dog, labeled as forest, because the two parts of the network don't actually know what the other part is doing, right? So neither of these parts, necessarily is making a bad guess or is making a wrong guess. But when we put them together, it's clearly wrong because they're trying to accomplish different things. Does that make sense? Okay. So moving on from classification plus localization, we want to go to types of models that try to more intelligently combine these two tasks together so that we can be sure that the model is actually predicting the location and the content of the same thing within the image. So when we go to object detection, they're designed in a way that we can be a little bit more sure of that. So the object detection task is also harder because we don't know the number of objects that we're trying to find in the image ahead of time. So it might be one cat, it might be 2 cats, it might be a litter of cats. We still need to be able to identify each of them and draw a box around them. It could also be a mix of different things. So in general, object detection relies on a 2-stage process. The first is called object proposal, and the second is called object classification. So object proposal is where we draw bounding boxes and say, I think this might be something that's worth flagging. And then the object classification step is trying to identify what it is that is in that part of the image. And we combine that together and make a prediction. Now, there are 2 main families of models for object detection. The first is called single stage. This is confusingly named, actually. So these are called single stage and 2-stage, but they actually both do both of these things. So it's easy to get mixed up here and think that single stage must skip one of these steps. The distinction is actually whether they happen in parallel or whether one happens and then the other one happens. So in a single stage system, we do object proposal and object classification at the same time, and then we decide which of them we think are worth sort of providing as predictions. Whereas in 2-stage, we first do the object proposal, and then we predict the class within each of those sections. and provide that as the prediction. So what does that look like in practice? YOLO is the sort of earliest big success story in this object detection space. It's called You Only Look Once. 2016 is when people were saying YOLO or, just about getting tired of it. So I guess it seemed funny at the time. Um, the big value here is that this is actually a model that runs very quickly. So the reason that they are doing this as a one-stage problem is so that the predictions can be made fast. And that means that this system can be run in real time. So it's useful for things like live prediction. And so the way that YOLO works, you'll see that even though we call it one stage, it is doing both of these things, but they're happening simultaneously to one another. So for our input image, what we do is we divide it up into a grid. And then in the classification side, we take each part of that grid and we make a prediction about what is in that section. Some of these are going to be really bad guesses because we can't really tell what is in that part of the image. So like some of these parts down here, there's nothing going on here and it's going to have a hard time, but we're still making it make a prediction because we haven't decided yet where the things are that are in the image. So here what we have is what we call a class probability map. And this is, an attempt to say for every single part of the image, what is in that part. So, we can make a guess that blue is belonging to dog, yellow is bicycle, pink up here is car. I don't know what green refers to, and maybe red is just like the ground as a class. So that happens. And then at the same time, we predict any number of bounding boxes in the image. And so this number of bounding boxes is set beforehand. It's sort of like a maximum number. And so, maybe this is usually like a high number. So maybe it's 50, maybe it's 100. And we're going to predict everything that we can possibly find in the image that could conceivably be an object. So what you can see here, it's a little bit hard to tell, but the boxes in this image have a different thickness, and that thickness corresponds to how confident the model is in that being a real thing that it should be, predicting. So we can see in this example, the thing it's actually most confident about is this car up in the top right corner. That's the thing that it has the thickest box around. And then the bicycle and the dog are also ones that it's highlighting. So then what we do is we combine these two things together, and there is a confidence associated with the prediction in each of these boxes. And there's also a confidence associated with these bounding boxes up above. And so what we do when we recombine these is we say, okay, now combining these probabilities, these confidence values, what are the things that overall we're most confident in? I see a few people are asking, how are the bounding boxes generated? So this is that regression task, right? So we're predicting the four values that are the position and size of the bounding box, except now we're saying we're going to do like 50 of them or 100 of them. And for each of those bounding boxes, we also predict a confidence score, which is how likely it is that the thing we've drawn a bounding box around is actually a subject in the image versus just like some random thing. So these parts do sort of work the same way as before. It's just the way that we combine them that is now different. And so once we've done these steps, we then multiply the class by the probability, by the confidence that we have in our bounding boxes, and we check if that meets some threshold. So when we combine this classification with the bounding box, is that total prediction something that we have above a certain threshold? And ultimately, what we provide out as the prediction is every pair of bounding boxes and classes that has a high probability to it. So just to, really drive that home, we have this value, which is a class probability. And so we want this probability to be high. If I think, this is red, but I only have a 20% chance of it, that's a low probability, and it's unlikely we're going to predict that there's an object there. And then at the same time, we have this confidence value up here, and that is coming into this section, which is saying how likely is it that this is actually a bounding box around something significant. And so when we combine this probability with this confidence, we essentially get a combined value of how likely it is that there is a thing and a thing that we're able to identify in this part of the image. And so that ends up in this case with our three bounding boxes that are the car, the bicycle, and the dog. Any questions on that? I know it's a little complicated. Yeah, go ahead, Sneha.
How do we define classes? I mean, like we will be having so many different images, and in those images, we'll have tons of different objects. So in classes, we already know that there will be a dog or maybe there will be a cat. So what is the limit of the definition of classes?
Yeah, so it's the same thing here where we have to predefine all of the possible classes that we might want to predict from. And we train the model to learn examples of each of those classes, right? So there is a fixed set of things that this model is able to identify the class for. So in this case, we would imagine that dog and bicycle and car are all things that the model has been trained to identify, and that there is a class value corresponding to those things. Going back, oh, maybe I don't have something relevant. Oh yeah, I was just going to say, the C classes here, it's the same thing. The set of classes is something that we have to decide before we train this model. So there isn't an unlimited ability to predict different kinds of things. It's fixed as part of the model training.
But like uh, this is valid when we are doing the training. What if we are testing the model on the images which we don't have beforehand, right?
Yeah,
That's where the model validation, the testing of the model will be valid.
yeah, that's right. But we've trained the model on in order to predict these possible classes. So let's say it's dog, cat, and capybara. If we train it to identify those three things, it's not capable of predicting anything else because the output of the model is only three values that correspond to those three possible things. So either it's true or false for those three categories. There's no way for the model to express to us that it's seen something else. It's definitionally not able to do that.
So this is one of the limitations of this model, right?
Yes, absolutely. Um, in in newer vision language models, which we use in assignment 2, they don't have this restriction, right? Because they actually have a language component, so they can conceivably predict anything that we can describe in language. Their capabilities may not mean that they can do that in practice, but in theory, as long as you can describe something, you can then look for that in an image using a vision language model. And that's what we work through in assignment 2. So that is a much newer approach, and it's not something that these models were capable of doing at this time.
Okay, thank you.
No problem. And Kevin, I see you also have your hand up.
Yeah, I think I'm just answering what Sneha's asking, right? I mean, like, I don't know, let's say you have rhinoceros, right? Uh, I don't know, imagine it, right? Back in 2012, obviously it's trained with all the existing images at that point of time, some millions, right? So I'm not agreeing that word, like what you guys are like saying it's a limitation. It's like saying, what if you don't have a word in English, right? Yeah, sure. If it's exotic animal, sure. But 99%, the model is trained with all the words, all the text in the world, right? In the internet. So same with
Mhm.
the images too, right? So uh, in terms of limitation, that's not the limitation. Actually, limitation is in terms of the performance. The transformers have some benefit, but unless it's exotic animal, I'm sure this CNN model will able to identify the all the existing images. So I don't know. That's my point of view.
Yeah, I appreciate that. You're absolutely right. This is like a fundamental, fact of how these models are built, that they're not able to, predict things that they haven't been shown before. There's a couple of comments that I wanted to go through. So Vinod says that the prediction for all of these things are based on the cells of the final convolutional feature map. Yes, exactly. So just like on this slide, the first thing that we do is we feed our image into a convolutional neural network, and we get this output feature map here, which is what we're going to use to make our predictions. And so, yesterday I made the analogy that this is almost like building an embedding. It's creating a new representation of the image that sort of gives us a sense of what is happening in that image in an abstract way that the model knows how to work with. So you can think of this as creating an embedding for this specific image, and then we use that embedding to actually make our predictions. And just like that model, what we're not showing here is that there's going to be a CNN that actually takes the image as input and then is fed to these two different parts. And then Christian says, would it make sense to not make it a parallel process, but instead generate bounding boxes first and then pass the most confident ones to the class identifier? Yeah, so that is the two-stage process. And the two-stage process is a little bit more intuitive, that it sort of makes sense to do it that way. In practice, we find that both of these actually work really well. So doing it in parallel or doing it in sequence, we get good results either way. But there are some benefits to the two-stage process, and I will talk about that next, I think. Yes, I will. Okay, so instead of having this sort of predefined set of box proposals, we can find them on the image, right? So we can do selective search where we find them based on pixels. We don't do that anymore. Instead, what is more common is the RCNN or region proposal network. And I have a slide. The next slide is going to show visually what this actually means. We do something that is called crop and resize. So we take a convolutional map as input plus our regions of interest. We make these predictions, and the idea here is that we're only making predictions on the regions that we have suspected might be containing a subject, and then we only update our weights relative to those sections. This is going to make a lot more sense on the next slide. I just want to quickly answer, Vinod has a question. Have we moved from faster RCNN to YOLO these days? Are they both in use? YOLO is one of the most commonly used models for this type of thing. I think we're on YOLO v3 or v4 or v5 at this point. But yeah, it's definitely something that is commonly used even today. Kevin says CNN itself is obsolete. That's actually not something I would agree with. So transformer-based networks are currently the state of the art. So there is a different approach, that we use in like vision language models that has been shown to be highly effective for vision-based problems. But the CNN is a really basic operation, and there's a lot of research into how we can integrate CNNs into transformer-based networks. There's no reason that we can't take advantage of both of these technologies together. They're not exclusive to one another. So a lot of what has already happened with convolutional networks has definitely been superseded by these newer transformer models, but there's still a lot of active exploration of how we can combine the two. And I would suspect that is the future for vision.
On
Okay.
a side note, you agree that at least RNN is kind of obsolete when it comes to transformer, or you don't agree that?
This faster RCNN, I would say, is obsolete now, but this is an interesting and worthwhile thing to understand, because there's some real value in terms of how we train the network that can apply to more than just vision. So there is some really important stuff to understand in how this is designed. Yeah, so I mean, again, the convolution is this really, really basic concept that we can have a set of weights that we reuse all over the network to look for a pattern. That is not going to go away. convolutional neural networks, as we think of them, are being beaten in performance by transformers. But we want to be specific about what exactly has changed here. And what's changed is that there's this new field that is currently doing really well. But there's no reason we can't combine the two. All right. So how does this work? Just like the other models I've shown you, we start with a set of convolutional layers that extract features from the image. This again is like our embedding. And what we have here is a representation of that embedding of our feature maps coming out. Then what we do is we run what is called the region proposal network. And the region proposal network, just like in YOLO, is going to try to predict which parts of the image are likely to have an object in them that we care about. So this in many ways works the same way. The difference is in YOLO, we also at the same time are making a prediction about every single part of the image and what is contained within that part of the image. But in faster RCNN, what we do is we only make predictions within these boxes. So everything that's outside one of these boxes gets ignored by the classifier. And you can essentially think of like what we're doing here is just cutting out the regions of this feature map that the region proposal network has selected. So that's why we sort of see this is also passed up here, is because it's cutting out those regions and it's using them to make a prediction. Now, the value of doing it this way is that when we then do backpropagation, we're not updating the parameters based on the really bad predictions that are being made in these parts of the image where nothing is going on. Because here we are forced to make a prediction for every part of the image, we're also updating the quality or the parameters based on our very low information predictions about some of these boxes. And that is almost like a waste of time. We're updating based on something that we know is not going to be very useful for our model, because ultimately this isn't being used for anything in our final prediction. So for faster RCNN, because we are cutting out these regions and we're only classifying within them, we're essentially able to improve the quality of that classifier faster than what YOLO is able to accomplish. So, in practice, we have to do sort of like a combined metric here because we're doing both classification and the regression of finding these bounding boxes. The typical metric that is used is called mean average precision at a given IOU threshold. And so the idea here is that we evaluate the quality of the classification, but only when the bounding box is sufficiently overlapping with the real answer. So, first we say, is the bounding box a good bounding box? And if it is, then we compare what we predicted in that area with the real answer. But this way, we're not comparing every single bounding box in the image with the real values. If it's nowhere close to the right area, then we just assume it's a bad prediction, and we don't need to evaluate the classification accuracy. The state of the art here, again, Papers with Code is a great website for going and having a look at what is currently going on in the field. I strongly suspect that if I follow through on this link right now, that it will be a transformer-based method that is, achieving the best performance on this task. But the field is in flux, and the things that people work on are continuing to change and get better and worse in different ways. Actually, why don't we take a look? Let's see what is in here. Here, I'll reshare my screen so you can see as well. Okay, so if you haven't been on Papers with Code before, this is what it looks like. So you can go and you can find a specific task and on a specific data set. So this is COCO, which is the Microsoft Common Objects in Context data set. So pictures of things in the normal context that they exist in. And we get this nice plot that shows us how different submissions have sort of continued to improve over time. So each of the gray dots is a paper that somebody published on a new method. And then the blue is the best performing method over time. And so you can see, this only starts in 2017. That's when people started, doing this task at all. And that faster RCNN was like one of the earliest methods that was really effective for this task. And over time, we've seen newer and newer methods get this prediction accuracy higher and higher. And it seems like the most recent submission that actually beats the state of the art is actually from 2023. So it's been a couple of years since somebody has significantly improved upon this. Or this actually says 2022. And so we can click on this. It will take us to the paper. We can also click here to go and visit the code. I will take a look at that maybe during the break and then come back and see if I can talk about what that paper does, just if people are interested. But now I think we can go back to the slides. Okay, just gotta re-share that. Okay, great. Yeah, so really great website for finding out about what's going on. In the break, I'll take a look and I'll see if there's something interesting to talk about there. Okay, so that is object detection, but again, we can go further. So beyond object detection is segmentation. And for segmentation, we don't just draw a bounding box around the part of the image that we're classifying, but we actually say exactly pixel by pixel where that thing is in the image. And so the way that we do this is, we're outputting a class map for each pixel in the image. So if we're saying that this is dog, then we're saying that everything else is background, and we're able to separate it that way. And then, going beyond this segmentation task is instance segmentation, where, even if there's two different dogs in the image, we're able to say that those are two different things as well. And it is possible to do instance segmentation through a combination of object detection, like in the previous task, and then segmentation. So in the first step, we sort of, we just draw a general bounding box around each object in the image. And then once we have those bounding boxes, it's a lot easier to perform the segmentation task because we only have to decide about what's going on specifically in that box. So that's an effective approach. And this is where we get to this idea of the fully convolutional network. So here what we do is we slide the entire network over a larger image, and the output of this image or of this network is going to correspond to a pixel by pixel prediction of what is in the very center pixel in that part of the image. So if we are, looking at this region, then we're only making a prediction for like the central pixel here. And as we move this over and over gradually, we will make a single by single prediction about what that center pixel belongs to. And so what this allows us to do is build, if here we're looking for tabby cat, then for the entire image, we can make a prediction of which pixels belong to tabby cat and which ones don't. And so this is the idea of the fully convolutional network. Because we go down to a one-by-one convolution, we never need to flatten and then do a separate classification task. In summary, when we do this, we want to predict for every output pixel in the entire input image, and we might aggregate different feature maps together in order to recognize patterns at different layers of complexity. But what this allows us to do is make this very sophisticated segmentation that labels every part of the image as being some kind of class. And there is a faster RCNN version of this approach as well. So here we do the same thing that we did before, where we make these region proposals and we classify within them. But then we also add these RCNN, or sorry, these convolutional layers that predict pixel by pixel within those image regions. So again, it's a little bit faster because we only have to consider this specific class in this specific region. We already know that that class is in that region. We just have to find out exactly where. And so The results of this are, fairly impressive. This is from 2017, and it's only gotten better since then. And you can see what I was talking about how we both have a bounding box and a more specific segmentation within that bounding box. So we first predict, we know there's a motorcycle in this box, and then only looking at that box, we can say pixel by pixel which actually belong to the motorcycle. And yeah, this works really effectively at describing what's going on in one of these images. And this is just more examples of that as well. So again, the TensorFlow and PyTorch both have various implementations of how to do these object detection methods. This Detectron library for PyTorch, developed by Facebook Research, implements many of these vision methods in a way that makes them very easy to use, and you can download the weights as well to run pre-trained models. There's a number of different benchmarks in computer vision, different tasks that people work on that you can compare against. And so, this wraps up sort of the lecture side on computer vision specifically. And so some of the takeaways that we'll want to think about, in more than just computer vision, so tomorrow and then moving on, are this idea of using pre-trained features as a basis for our network. So, this is useful in more than just computer vision, where we want to take a pre-trained network that already has very useful pattern recognition for the type of thing we're dealing with, and take advantage of that when focusing on some new task that we've never done before. So, ImageNet is a very popular place to start when it comes to computer vision. There are a huge number of images, and they're all labeled nicely, so you're able to start from a good place. And then, yeah, the network that you choose is also going to have a major impact. Both of these are fairly old networks now, and in the modern space, transformer-based networks are generally where people start off with. And so, yeah, once you have one of these pre-trained networks, you then go to fine-tuning, where you add additional layers on top of the existing network that are specific to the task that you want to work on. And then you can either, as it says here, fine-tune the entire thing, so train the entire thing, or you can freeze this earlier part and just train the part that you've added on, which is going to be a lot easier computationally. And so, one thing that is very popular to do is to, start with a pre-trained model on something like ImageNet, where it's just a basic classification task. But then once you use that model, you can then go to a smaller but much more exhaustive or much more detailed data set. So, that has bounding boxes or masks, things that are actually quite time consuming to produce, but you don't need as many examples because it already has this basic understanding from the more simple task originally. Okay, a little bit of a shorter lecture tonight, but that's okay. We will take our 15-minute break, and then we'll come back at 7, and we'll get started on the labs. Just before we get started on the lab, I just wanted to share, I took a look at papers with code. So as we saw, the top model as of today in the object detection task here is this CoDeTer model. And I had a look at what it is. So DETR stands for detection transformer. So it is a transformer-based model. But what I thought was interesting is it's actually a combination of a convolutional neural network and a transformer-based network. So just like I was saying, there is an opportunity to use both of these things here. So I won't get into too much detail on this because honestly, I was only just reading the paper for the last few minutes. But the way that this essentially works is that first the image is transformed using a convolutional network. So we get that set of image features. And then that is fed into a transformer model, which produces a set of region proposals, just like FasterRCNN or YOLO does. And then those region proposals are used to predict a class and a bounding box, or alternatively saying there's nothing of note in that region after all. And so, the combination here, it predicts a fixed amount of regions every time, and then it chooses some of these to use at the end. This is actually slightly different from a vision transformer. A vision transformer feeds the image directly into the transformer section, and it does that by chopping up the image into small chunks, and then each of these small chunks would be one part of the image. Whereas here we actually do this CNN first. So, this is not part of the class. It was just something that I thought would be a little bit interesting because it's relevant to the discussion that we just had. Yeah. Okay, so let's go to the lab. Okay, so starting off, let's go through the last bit of Lab 4. There's not too much to talk about from Lab 4 tonight unless people have questions about it. There's just one part towards the end that I wanted to make sure that I covered. So we went through all of this, we did the blurring, we defined our own convolutional layer on the grayscale image. This is just one example of edge detection in both directions. We did our pooling examples, and then we got here where we asked you to use the pre-trained model to make a classification prediction on this cat image. And so last night I noticed that a lot of people were finding that this was that this didn't really work, right? I think Calvin just said something like that in the chat. There were some issues getting this to work the way that we would expect. These predictions clearly don't make sense for that picture of a cat. The good news is I was able to figure out the issue. And so the issue is actually in the scikit image resize function. So the original image, the original picture of the cat, has red, green, and blue values, and those values go between 0 and 255 as the highest value. So that's what we start with here. Now, when we run this resize function, which we think all that's going to do is just change the size of the image, it actually also changes those values to be between 0 and 1. So it divides them all by 255, which we didn't realize was also part of what was going on inside of this function, especially because it doesn't actually say that it's going to do that here. So the issue is that once we have resized this image to be between 0 and 1, which we didn't even realize we were doing this normalization, and then we feed it into this pre-process input, the combination of those means that the values end up being in this really weird range of negative 123 to negative 100. And this is what was causing the issues with this step. So it is what Calvin was saying in the chat. This is what would have caused the image to just be a black screen. And it's the reason that these are such bad predictions down here, and they're not what we expect at all. Now, the good news is it's one line to fix it. All we have to do is multiply the cat image by 255 after we perform the resize so that we bring it back to the original dimension that we wanted it to be. So if we multiply by 255, then when we run this, we will see that it brings it back to this acceptable range. And then when we pre-process, we get a range of negative 120 up to 87. And you'll see that once we have that, now we're getting a prediction that looks correct. So now with the model fixed, and by adding this one line, and Vinod just shared a equivalent version as well, now the model is giving us correct predictions. So Egyptian cat is 96, and then the two next best guesses, which are very low, are tiger, cat, and tabby. So model is working correctly. So I apologize about that. It truly is an example of making sure that you understand exactly what these functions do before you import them. And obviously we hadn't done that. So that's the reason why that wasn't working. And yeah, so if anyone has any further questions about that later, feel free to ask me, but adding in that one line will make it work. Okay, any other questions about Lab 4 before I move on to Lab 5? Okay, great. So Lab 5, we are going to build a simple object detection model, which is the sort of the first one that we talked about. So the classification plus localization as two different heads. The other models, which are more advanced, very quickly become ones that we can't really train on our personal computers, or it's difficult to. So that's why we're sticking with object detection here. We're going to use the Pascal VOC 2007 dataset. It contains pictures with bounding boxes and classes for 20 different objects. We're just going to stick with 5 of them to keep it simple. We also do need to install another library here just to make this work properly. So just run that if you haven't already. And we're going to use TensorFlow and Keras here. This says that you need a GPU. I ran this without a GPU, and I actually found that it worked okay. So don't worry about that if you don't have a GPU. Okay, so let's get started. First off, we're going to run this code that will automatically download the data set. It will extract the data, and then it will also download some additional files that we're going to need later on. This does take a couple of minutes. I've already run it, which is why it just happened instantly, but I would recommend running that sooner rather than later. And then we're going to get started on actually building our classification and localization model. So the goal here is that we're going to build this model that has the 2 different prediction heads, the first of which is going to classify what the subject of the image is, and the second one is going to predict the position and size of the bounding box around some, what it thinks is the subject of the image. And this is a great example of, we can actually build really flexible neural networks with complex and interesting designs, including ones that make multiple different predictions simultaneously about different aspects of the data that we're working on. And so there's 3 different steps that we want to do here. The first is to extract the data, right, from the data set. We have the label annotations in a kind of weird format in this data set, and we're going to pull that out. The second is that we're going to take a pre-trained image classification model, ResNet-50, and we are going to compute the features for all of our input images in advance. So because we are using this pre-trained ResNet-50 model, and because we're not training that part of the network, we can actually be clever and compute all of the features for all of our images before we even run our main neural network. And then what we'll actually do is we'll feed in those pre-computed features as our input instead of the original image. So, linking this back to embeddings, it's like starting with the embeddings instead of the words. We're giving it this starting point that is more informative than if we had to actually go all the way from the raw image input through ResNet-50 to the part of our model that we're actually training. Yeah, this is transfer learning. Yeah, so we're transferring what's already been learned from the ResNet-50 model, and we're taking advantage of that in our new setting. And so once we've done that, we are then going to design and train a baseline object detection model that is going to show us just the very simple structure of how we build this network. And then lastly, we'll build together, a more full version of the model that will actually do some convolutions and make these predictions. I see that someone got an error. Okay, it looks like I'm wondering if they have changed the syntax for the tar file.
Actually, it says extract all, right? It is not expecting filter, but in signature it is there is a filter. I mean, that's the error actually for the extract all.
So if you delete filter equals data, it works?
I didn't try, but there is a signature. It expects a filter, but I'll try that. But
Yeah, so
the
since it's saying that it got an unexpected keyword argument filter, the first thing I would try is just removing that and seeing if it's still
Yeah, it's working actually.
Okay, great. So if you're getting that error, just delete the filter equals data. Yeah, hi, Aya.
Hi, I have a question about transfer learning.
Mhm.
What I know about transfer learning currently is that if a model is, trained on like a data set and it makes good predictions, and then you introduce new classes for a model to make predictions about, but sometimes it will fail to make uh, like maintain the accuracy that it had about the previous classes. Is that something that we would need to consider currently for this work, or like when is that really an issue in the incoming classes or set of classes are is bigger than the one that was trained on, or like we need to consider this at all?
Yeah, so that's a great question. So just to summarize for anyone else is my understanding of the question is that there's this phenomenon where when we retrain a pre-trained network on new additional classes that go beyond what it was originally trained with, it can sometimes fail to sort of achieve the same performance on those new classes that it did on the original, even if we would otherwise expect it to do just as well. That is true. That is a risk with transfer learning. And so sort of the reason that that happens is that, the entire network has been trained with the expectation that it needs to learn patterns that are specific to these classes that were in the original data set. And so if we then go and add new classes that are very different from the original, it doesn't have the patterns in the model that would be necessary to sort of go out and correctly identify those classes right away. But because we're now doing transfer learning, where we typically use a smaller data set and a smaller learning rate, we're not giving it the opportunity to completely relearn from the ground up what it would need to be able to accomplish for those new classes, what it was able to accomplish for the old classes. So if I was in that situation, oh yeah, go ahead, please.
Sorry, I thought this phenomenon was that it would start to forget how to make predictions about classes that it was trained on originally, not the new ones that it is learning.
Oh,
Like it
you're
starts to
saying
like
it's
regress in performance.
right, right. So you're saying it's getting worse on the old ones.
Yeah.
Okay.
Or is that like a niche case that never happens? Like it rarely happens.
That can happen too. Yeah, where essentially it's overwriting the old ones. It depends again, like so the reason I was assuming that we were talking about it failing to learn for the new classes. And the reason that that would happen is because it's already trained on the old classes and there's not enough learning happening on the new examples. Where you're talking about is the other end of the problem. So if we have the learning rate too high in transfer learning, when we do the fine tuning, then it might essentially overwrite what was originally learned with a new set of patterns, with a new set of rules, and then that would cause it to forget what it originally learned. And so what we need when we do transfer learning is to sort of find a balance in the middle where we want to update some of the network so that it's additionally able to, handle the new examples, but not so much that it loses that ability. And that's part of the reason that we try to keep that learning rate low during fine tuning. So we're just making small adjustments. And yeah, we have to be very careful when we do it to make sure that we don't go too far in the other direction. So yeah, great question. Yeah, so just I'll call you in a second, Kevin. I just want to make sure that people in the chat understand what's going on here. If you're getting errors with this line of code, then the alternative, which seems to be working for people, is just to do this without the filter equals data. So try this if it's failing.
But actually, if you hover the extract all, right, there's a filter signature. Hover over the extract all, you would see it is expecting filter. I don't know why it's getting complaining then, but it's working though without filter.
So I think what's happening, the reason that we have this is because we're in this tar file is more than just the data that we want to work with. There's other stuff in there as well. And so this is basically saying we only want to do this part. But it seems like some people have a different version of this Python package where it doesn't have this parameter. And so if that's failing for you, just remove it. And so don't have both of these, but just one or the other, and then that should work. Okay, so hopefully people are able to get that part to work, and if not, we can come back to it later. But now we're gonna start working with this data. So yeah, this data is in a very complicated format in the data set, and so that's why we've sort of written this for you to handle processing into something that we are going to be more familiar with. So here we're sort of we're loading that data and we're pulling out, this is our bounding box coordinates. So here we have, like a bottom left and a top right coordinate that defines the box around whatever the subject is. And then we're also, we're doing that for every object. And each object has a corresponding file name and a size. And so here, what we want to do is we just want to filter for these 5 objects. This is actually 6. No, it's 5, sorry. We want to filter for these 5 objects. And we are going to go through all of the data and look for the images that contain one of these 5. And if we find them, and there's just one object, because some of these images have multiple objects, we will save the pictures that have a single object in them. Okay, so when we run that, we find that we end up with 1,264 images. And this is an example of what the actual annotation is going to look like. So, here we have the class is car, and we have a bounding box that goes from the bottom left to the top right of the bounding box. And here is the image that corresponds to that. And so indeed, it does show us a car. And then we have a little function here that even shows us what it looks like to draw the bounding box. And so this is what we want to predict, is, what is it and where is it in the image? And yeah, we can see that 0 through 4 are the options, and this is what they correspond to. Okay, so like I said, we're going to build a network that first uses the pre-trained ResNet 50 model trained on ImageNet, and then that we pass the feature maps from that ResNet 50 model to the part that we're actually going to build. And so, we can load our ResNet 50 model here. We're going to remove the last couple of layers in order to do that. Yeah, go ahead, Kevin.
Sorry, because I keep saying that the transfer learning, right? So my understanding of transfer learning is, so basically you take the ResNet or VGG 16, right? And you chop off the top layer, the last layer, and then you use let's say I'm trying to, I don't know, classify, like I have only, I don't know, 1K data set, right? Obviously, I don't have the data set to train my 1K. So I use either VG16 or, ResNet, right? And then chop off the top layer and then use my 1K. So I don't think there's extra training. You already had pre-trained model, whatever the deep neural network, you're just using it, right? So there's no pre-training again, there's no learning it again. You're already using, it's like, I don't know, you're just buying a pizza and just warm it up and eat it, right? So you're not really making, again, that's my understanding. So I don't know.
Yeah, you're pretty much there. I mean, the reason that we use this term pre-trained is because someone else already trained the network, right? So it already has weights that correspond to identifying patterns that we want to be able to identify in the image, and that's the thing that we're taking advantage of. Vinod says we're fine.
Sorry, again, there is no fine. That's what we're getting terms and mixed up. Even
Yeah.
we know the same fine tuning. We are not fine tuning. That's why my point of view is
yes.
We don't fine tune. We just take as is and use that whatever the information the deep neural network, right? And then we just use it to identify. That's what my understanding is. So
yeah, you're absolutely right, Kevin. So Vinod, you're slightly off. We're not fine tuning here because if we were fine tuning, we would also be updating the weights of this ResNet 50 model. So if we were training the whole thing end to end, that would be fine tuning. But here we are actually just using the ResNet 50 model as it already exists. And then we are going to go ahead and train the rest of the model. Yeah, so it's the equivalent of us freezing the weights of this ResNet 50 model. We're making no changes to this. We're just using it as it is.
thank you. So I just want to get the right understanding because thanks.
we are loading this model, and then we are going to predict on each of our input images so that we get the output features that this ResNet 50 model provides for us. And when we do that, so this is, our sample image of a cat. If we do that, then we get an output that is 32 by 7 by 2048. So we have 2048 different, output grids that are of size 32 by 7. And that's sort of the output of this model for this picture of a cat. Yeah, so this is the result that we have here. The reason that it's 32 by 7 is because this image is wider than it is tall. And so that's why it's not the same number in each of these. So you see the math here. Okay, now, if we were to run our ResNet 50 model on all of our images, it would take a bit of time. So instead, what we've done is we've actually done that for you already. We've downloaded it, and we're just going to load that data into the system here. So, this is really just to save time. What we could have done is run this predict batch on all of our data that we're working with, and we would get the same result as what we're doing here. And so what we have is for every image in our data set, so all of our, how many was it? Like 1,264 images, we are going to have the output of this ResNet 50 model, which is what we're actually going to then use when it comes to training our data set, our model. And we can verify that by checking that this is short for representations. And yeah, 1,264, and it's 7 by 7 pixels because this is a smaller image than this picture of a cat. But just like the picture of the cat, we have 2,048 different values for each of those grid values. Just checking some of the things in the chat. If you're running out of memory, then what we can do is try to reduce the amount of data that you're loading into your system. So where is it? So here we are loading into our system this set of 1,264 images. If you find that this causes you to crash, if this is too much data, what we can do is we can add something in here that stops us after a smaller number of images. So this works by adding annotations or adding images one at a time as we find ones that we like. So what we could do is we could say if the len of annotations is greater than or equal to 500, for example, then stop. And so if you do this, then you'll only have 500 images, for example. So if you're finding that it's crashing because you're running out of memory, add these extra couple of lines here. If we already have 500 images, then we're going to stop adding any more. You could make this even smaller if you needed to. Just reduce that number until you find something that works for your system. And I'll copy and paste this into the chat so that I can move on. I'm going to take that out for me, but if you find that you need that, please feel free to do that. Okay. And if you do that, you will also need to do the same thing here. So if you have, for example, 125 images, then you need to do, let me check that that's right. Yeah, that's right. Okay. You'll need to replace this with just the first 125 or something like that. So I'll copy and paste this into the chat as well. And again, this is only if you're finding that it's crashing. But for me, I'm gonna keep them all just for the demonstration's sake. Okay, so now we have, yeah, you can also use Google Colab and it won't crash in there. But if you need to run it locally, you can add those lines. Okay, so now we have these feature maps for our 1,264 images. We have 1,264 images, and for each of those images, we have 2,048 feature maps that are 7 by 7. And that is what we're actually going to use to train our model. And remember, these correspond back to the original images. So that's what we're working with here. Now we are going to build our labels that we actually want to tell our model to predict. And this is essentially going to be our coordinate values. So that's being run for us. And so this is an example of what that looks like. We have 5 possible classes, and we have a bounding box that contains 4 values. In our first 2 classes, for example, it's whatever the 4th class is. I think it's car. I got it right. It's car. So these first 2 images are pictures of cars. And then we can confirm that the box coordinates also sort of look like what we would expect as well. And so remember, it's the bottom left corner and then the top right corner of where that subject is in the image. And we're also going to build a function that will sort of let us see the output of the model in a way that is easier for us to understand. Okay, so just to check that everything looks like what we expect, here's an example of our interpretation method here running on the output. And so this is sort of the thing that we are going to see is we've predicted class car, we have confidence 100%, and there's a bounding box of where that car is in the image. Okay, we're almost at training our model. The very last thing I think that we need to do is write a method that computes this intersection over union. And so remember, the intersection is the area of the overlapping shape between the 2 bounding boxes, and then the union is like the combined shapes area. And we want those to be the same. And so here are some different tests where these are exactly overlapping, these don't overlap at all, and these overlap for the most part, but not exactly, and we get values like what we would expect to see. Okay, let's build our first classification and localization model. So this model is basic, but it's going to show us the structure that we need to understand for this task. So it's going to take in as input our feature map, so our 2048 7 by 7 grids of features in the image, and we're going to do this global average pooling 2D, which is a flattening operation that's going to turn it from 2 dimensions to 1 dimension. And remember, in here is where we're going to put our convolutions when we go down to later. So we are actually not doing any convolutions here. We're just sort of demonstrating the structure, but the convolutions go here. And then the next layer is a flattening operation. So, you could replace this with flatten just to go from 2D to 1D. We've got that instead. And then here is the part that is a bit different to what we've done before. So you'll see we're not using the model.sequential. We're doing things slightly differently. And the reason that we're doing that is because we actually have 2 different heads, one for the class prediction and one for the bounding box prediction. And they both take the output of this part as their input. So they both take this X value and they do different things with it. So this is where we have our branching point. Rather than doing all these things in sequence, these are actually now happening separate to one another. And so our class prediction head is going to take in the output of this section, and it's going to predict which of the classes this image belongs to. And then the box prediction head is going to also take in this section, but it's going to predict those 4 bounding box values that correspond to the size and location of the bounding box. Now, in this model, we want to output both the class and the bounding box, right? And so correspondingly, in this section, we are going to say that we have 2 different outputs. We have the output of the class prediction head and the output of the box prediction head. So this is new to us. We're not giving 1 output, we're giving 2 outputs. And because we have 2 outputs, we also have to have 2 different loss functions because it's going to compute the loss separately for each of these 2 values. The very last thing before we can go ahead and run this is that we're going to multiply the second loss, the mean squared error, by 0.0001. And the reason we're doing that is because if we don't do that, then numerically, this is just going to be a much larger number than this is going to be. Because they're completely different loss functions, they do different things. What we're going to end up with is that this mean squared error is just going to be a lot higher. And we want them to be kind of in the same range so that during training, they're treated as being equally important as part of the model. I hear that some people are having issues with the kernel crashing. If you're finding that the kernel is crashing, maybe just watch along on the screen for now. There's going to be more time tonight for breakout groups anyway, because I'm getting close to the end of this. So there's going to be at least half an hour with me, plus half an hour with the learning supports. So if you're finding if it's still crashing, there's time for us to work it out. Okay, so that is going to build our model. It's called a bad model because we're not doing any convolutions. It's actually still going to be okay. And yeah, so this has 2 different heads that are going to do 2 different things at the end. That's just verifying that it works. We're checking that we have about the same number of examples for all of our classes. We actually don't, but that's fine. And now it's time to train the model. And so as this trains, you'll see that we have these 2 different classification and regression losses. And so we can actually track how the model improves separately for each of those. And here you're seeing exactly why I multiplied this value by 0.001, because you can see that it's much, much larger than the classification loss. And so the total loss here is just the sum of both of those when we multiply this by that modification value. And so we can see that over the course of 10 epochs, the total loss does go down. It goes from 3.32 or 3.33 to 0.82. Jennifer asks, are the 2 losses added before backpropagation? They are added before backpropagation in this case. So the backprop is still going to happen with a single loss, I believe, that mathematically that's going to be how it works. If we want the backpropagation to happen separately for each of those loss functions, then we need to train the model once with one of them and then once with the other one of them, which we're not going to do here. So really good question. And I might need to check that I'm right on that, but I believe that's how it works. And we can see that we get our errors, our loss functions for both of these separately as well as the loss together. And we can see that over the course of these 10 epochs that the classification loss improves more than the bounding box loss does. It might just be the case that if we train it for longer, we would get a good result on both. I'm not too worried about that. And now we can actually use our model to make a prediction and see how it is. So again, we're calling this the bad model. And correspondingly, we see that the bounding boxes are not very good. So it is correct that this is a dog, but it is incorrect as to where the dog is in the image. So there's only a slight overlap. This bounding box could be a lot better. We try for another image. Again, it correctly predicts that this is a picture of a car, but it incorrectly predicts where in the image that car is. And I believe that this is because our model is not complex enough to handle the task. We can compute the accuracy and the IOU and see how our model performs. So if we run that here, we can see that our class accuracy is high, but our intersection over union is very low, which sort of corresponds to what we see in the images there. If we run on more examples, hopefully it'll get a little bit better. So running on more examples, now our classification accuracy is really good. Our testing accuracy on the classification task is 0.929, but our intersection over union is still low. Now it's better than it was before, but this is like an average of 30% overlap between our prediction and the correct answer. Okay, so the very last part of the lab here is going to task you with building a better model that gets better performance. I'm going to take a stab at it here before we go to the breakout groups, but I encourage you to work on this further than I do. So remember, the first thing that we're going to want to do is apply some layers that go directly on the input of the model takes in the feature outputs from ResNet. So we want to do some operations on that before we split off onto our two separate layers. And then once we have split off onto our two separate sections, we'll do some further operations after that. So here, let's do some convolutions. Let's say we're going to do a convolutional layer with kernel size of 3, padding equals same, and we'll do a ReLU activation. And that's going to take our model input, do some dropout, and then we'll do that global average pooling layer that I used above. And this is like a flattening operation. So that's me adding some stuff that works directly on the model input here. And then down here, we are going to build our class prediction heads. I'm just going to use the same ones from before, but you can add more layers that work just individually on each of these parts. So you could add like another layer here that also just worked for the class prediction if you wanted to. And this is going to be 4 values for the bounding box. We want a sigmoid activation function, I think, or maybe we don't. What did we use? I think they're real valued, actually. Yeah, we didn't use sigmoid. Okay. So no activation function. I guess we could use ReLU here because we don't want negative values. Okay. And then those are going to work here just like before. All right. So my model, I'm only adding in one convolutional layer. I'm adding in some dropout, and then I'm doing everything else as before. I would recommend that you try more than this. Try adding some more dense layers down here. Try adding some more or some different convolutional layers up here. And then, oh, I might have to take a look at why that's happening. Well, I don't want to waste your time with me debugging this code, but this is essentially what we would like you to do. I will figure out why this happened and make sure that I can share it with people. But I don't want to sit around while I'm figuring that out. We'll ask you to train your own model and see if you can get better performance than the not very good model up here, at least in terms of the bounding box prediction. And the last sort of thing that I'll point out is, the classification accuracy here is really good. So when you're building this, I would say focus more on how can I fix this bounding box. So that might need more layers, but the classification stuff is probably pretty good as it is already. Okay. Oh, and Vinod says, yeah, the individual losses are combined into a single loss. So it is what I was saying before. They get added up, and then that single loss is used for back propagation. Okay, I'm going to create the breakout groups now, and please, go ahead and get started. I know that some people have some issues with crashing and things like that. So I and the learning support will be joining the breakout rooms and we'll try to help you figure that out. I'm also going to make sure that I understand what went wrong with my own code here so that I can make sure that we can share that on to you if you encounter the same issues. Okay. Actually, could one of the learning support please create the breakout groups? Oh, thank you, Vinod. That's very nice.